Okay, guys, this is a recording kind of to show you guys now that we know how to do percent weight volume and molarity. There are some problems that tie the two together. So when we look at the equations, they're similar. They're both ways of expressing concentration. They both have moles of solute, not moles of solute. They both have solute on the top, and they both have, but one is mass and one is moles, and then they both have volume of the solution on the bottom, but in different units. So I'm going to show you kind of a strategy for doing these problems that I'd recommend. So when I read a question like this, they're asking me for molarity, so I know that I'm going to need to use the molarity equation. And I have 250 mils, and I have a 7% weight volume solution. So I'm going to ultimately end at molarity, but I'm going to start here with the percent weight volume and try to calculate my moles. So if I plug into this equation, I would put in my 7% from the question that's given. It's going to equal my mass of solute, which is going to be my X, but I'm just going to leave it in as a word. And then over my volume in milliliters, which it is, times 100. So again, I think I've showed you this. When I do these, I divide both sides by 100 right away. So that becomes 0.070 equals X over 250. So when I solve for X here, I'm going to get 17.5 grams of sodium chloride. But then I have to kind of remember I'm ultimately trying to get molarity here. So I like to put it into 3 columns. This is the column where I'm going to convert between my grams to mole. And then I'm also going to convert my milliliters to liters so that I can then plug in here and get molarity. So my grams, this is where I would use my mole map. I have 17.5 grams of sodium chloride. I know the molar mass from previous questions. It's just 22.99 for sodium plus 35.45 for chlorine gives me 58.44. So there's that many grams in 1 mole. So I have 0.29 moles of sodium chloride, and I'm going to be moving that over in just a second. And then my milliliters to liters, you guys can just move the decimal. I'm going to show you if you forget which way. We know there's 1,000 milliliters in a liter, so we're dividing, which moves it 3 to the left. So then I'm ready to just plug in. So this is kind of my in-between. So I'm trying to go from percent weight volume to molarity. So now I'm going to plug in my answer right here, my 0.29 mole over my volume, my 0.250 liters. And then I'm going to look at my original numbers for significant figures. I have 2 here and 2 here. I shouldn't have. I grabbed a 0 there that I don't want to have. So I would want to have 2 in my final answer, and then I end up with 1.2. And then the unit is either mole per liter, or you can write it as 1.2 capital M. Hi, sorry, I just had to pause it for a little bit. Now I'm going to just show you one more and then we're done and you guys can practice. So here's a problem. It's the reverse of the one we just did, where we're looking for percent weight volume. We have the volume of the solution in milliliters. So I have 500 mils. I have a 0.25 molar, and we're looking for a percent weight volume. So we're trying to end here, but we're going to have to use the molarity equation to start. So when I do this, I am going to, let's sub into this equation. So again, I recommend that you kind of make 3 columns when you do these problems. So anytime you're going between percent weight volume and then molarity or the other way, I would recommend thinking of it like 3 kind of steps. So here I'm going to just plug in. So I have 0.25 I'm going to use black. Molarity equals, and I'm solving for moles, that's my X, over my volume in liters. I'm going to just put that work here. You don't have to show it anymore, but I would want to convert to liter. So there's 1,000 milliliters in 1 liter. So this ends up being 0.500 liter. So if you can just do that in your head if you want. But I'm going to put the 0.500 liter here. Then I'm going to solve for my X. And this is where you might want to cross multiply, however you would normally get your X. So for me, I'm going to take 0.25 big M, which by the way is moles per liter. I'm going to put the unit that way right now, because then you guys can see that the liters cancel and I'm ending with mole. So when I do that, I get 0.125 moles, and I'm not really worrying about sigs till the very end. Now that I have moles, I'm getting closer here. So I want to have mass, and I have the volume in liters, so I could even start this if I wanted, and then you kind of can see what you need. So I'm going to put, I do have my volume in milliliters, and the only thing missing now is the mass. So that's where I'm going to take my mole map out, and I'm going to take 1.125 moles, and it's calcium chloride this time, so I have a new molar mass. And the molar mass, if you do it with me, calcium is 40.08, and there's 2 chlorides, so 2 times 35.45, and then you should get, I think it's 110.98. So there's that many grams of calcium chloride in 1 mole of calcium chloride. So I'm going to put the grams on top and my mole on the bottom. And I'm going to put in calcium chloride just so everyone knows that that's what we're doing. And those cancel, so I end up with my grams. And this is where I'm not going to round yet. I'll round later, but I get about 13.8 grams. So now I'm going to sub that number in right here. And I'm just going to leave it in my calculator as is, divide it by 500, multiply by 100. And then now I'm going to look at sigs. I have 2 and I have 3, so I want to go with the least because I've been multiplying and dividing. That's the rule. So I end up with 2.8%. So we're going to talk about electrolytes. This is from 6.1 a little bit. An electrolyte is something that will conduct electricity if I put one of those conductivity meters in it. And the reason that it does is because it makes ions that are positive and negative, and the negatives and positives go and travel between the electrodes. So this is just a really kind of simple thing, but when you add an ionic compound like calcium chloride to water, it's going to break up. So if I ask you to do a dissociation equation, you're going to actually break it back into its ions. So there's really going to be calcium ions, and there's going to be chloride ions. And there's 2 chloride ions because of this too, but I bring it in front because literally I have, a calcium and then 2 chlorides. And I want to represent that. And the water's all around them, and this calcium is +2 and the chlorides are -1. I don't need to show it that way, but that's why we put the 2 in front. I'm going to put AQ here because this only happens when I add them to water. So for every 1 calcium chloride, I'm going to get 1 calcium, and 2, I'm reading the coefficients, chloride. So I can read that as atoms, I can read that as moles, and then I can also read it as molarities, because molarity is moles per liter. So I could say if I have 1 molarity of calcium chloride, then I'm going to get 1 mole per liter of calcium, and I'm going to get 2 moles per liter of chloride. So in this question, I have 0.25 molarity of calcium chloride. So again, I'm going to have this in a 1-to-1 ratio. So I would have 0.25 moles per liter of calcium ions, and then I would have double, because there's a 2 in front, I would get twice as many moles per liter of chloride. So if we were to do a problem together, this could be one. Let's do it together. If I take and dissociate, so you will break that calcium nitrate apart. So when I add it to water, it's going to break into calcium ions and nitrate ions. So if it's a poly, we're going to keep it together, and we bring the 3 with because that's part of what nitrate is, but we have 2 of them. So we're going to, because of this 2, bring it out in front. So in water, we really have a calcium ion and 2 nitrates, and then water all over in between. So it's kind of like this when you dissolve them. So now we're going to do just a little bit of math. So my question is, what are the molarity of the ions, so the concentration of the ions in a 0.75 molarity or molarity solution of calcium nitrate? So again, for every 1, I get 1. So I'm going to have 0.75 moles per liter of calcium. And for every 1, I'm going to get 2 or twice as many, which would be 1.50 moles per liter of nitrate ions. So once it breaks apart, I get 1 of these for every 2 of these up there. So essentially this is gone, because it's kind of like if I were to take like a crystal bowl and I break it, I drop it, and it breaks into 3 pieces. So it's no longer there. That's what happens once I add it to water. This is no longer there. It becomes this, the broken pieces. So then the question I might ask you, or what are the molarities of the ions? So you could say that the concentration of calcium, sometimes we use brackets to represent the concentration, is going to be 0.75, and the concentration of the nitrate ions is going to equal 1.50. So there's one, I'll do one more with you. So for this one, again, lots of polys here, but don't let that intimidate you. It's kind of like you're undoing the chemical formula. So we have ammonium, and we have 3 of those, and they're aqueous. So when they're in water, this is going to go away and break up into, and then we'll get 1 phosphite. So if I originally had a 1.5 molarity solution, then I'm going to look at that ratio again. I have 3, you can mathematically do it if you want, 3 NH4s for every 1 of the whole compound. So 3 times, you would just multiply 1.5 times 3 is 4.5. So there'd be 4.5 molarity of ammonium. And then you could again, mathematically, you had 1.5 of the whole compound. And then we have 1 phosphite for every 1, because there's a 1 in front of the ammonium phosphite. So the molarity of the phosphite is 1.5. You don't have to show the work, but if you're struggling at all. And then there's times where I might ask you, like, what is the total molarity of ions? You would then add these. You would ignore that beginning molarity, and it would just be the 4.5 that you get here plus the 1.5, which would be 6.